So today we discuss equipotential surface. Okay. So the important topic, equipotential surface. So what is equipotential surface? Actually, the concept of potential, you know that. Okay. What is potential and what is the relation between work, energy, and potential? Okay, we know that. Now we discuss the what is the equipotential surface. The name suggests that equipotential means same potential at the surface. Okay, if you choose a surface, the potential will be the same at any point on the surface. That's why this surface is called equipotential surface. Okay, the name suggests that very clearly. And see the diagram very carefully. There is a point plus q charge, and the red color is outward direction, means the electric field. We know that if a source charge is positive, so electric field is outward direction. Okay, and you see that another black color circular circle. This circle or circular path or circular line, actually this is actually a equipotential surface. Potential surface means the potential at point P here, the potential at point VP, the potential at that point VP, potential at that point VP, potential at that point also VP, the same actually. Okay, potential at the circumference at any point, if you choose the arbitrary any point, the potential value will be the same. That's why this surface is called equipotential surface. And you see that very carefully, the electric field piercing that surface in outward direction. If the source charge, if you choose a charge is positive, that is piercing the outward direction electric field. Okay, that surface is a equipotential surface. I know the potential is inversely proportional of 1 by r. The r is the radius of the surface circle. If I choose that a 2D diagram, so that is circle actually. So radius, if that is r1 and radius that is r2, and choose another radius, suppose that is r3. If radius is more, so potential will be the less, so they are inversely proportional. So if potential be the less, so we know that actually if r is much get any much bigger value, suppose that tends to infinite, so we know the potential at infinite be the zero. We know that. So actually potential is maximum the near the charge, the close to the charge. If r is very less, approx at that point here, very close. Okay, so that point potential be the maximum. If r is more, the potential actually that is a less. Okay, so here you see the r3 is suppose greater than r2, greater than r1, and potential that is v3, suppose that is v2, that is called v1. So v1 potential, if r is more, potential less, and r is less, potential more, so v1 is greater than v2, greater than v3. Clear the concept? What is the equipotential surface? Okay, so the electric field, that is inversely proportional 1 over r square, and potential is 1 over r. Electric field is a vector field. Okay, and that electric field actually the piercing that surface, they actually call it equipotential surface. So electric field piercing the equipotential surface means potential at that point on the surface be the same, any value, any point be the same. And now the next diagram, there is a two charge system, one is minus charge, other is a plus charge. And you know the electric field is outward for plus charge, minus charge with the inward. Okay, and at the cut point, okay, at point electric field in that direction, and that is the equipotential surface. And if both are in opposite polarity to charges, so see that the gap between two equipotential surface, okay, in opposite side of the plus charge, there is much more, suppose delta x2, that's called delta x1. So delta x2 is greater than delta x1. So that means if the polarity of two charges are different, in same way, in the front of the two charges there is a denser. Actually, equipotential surface is denser here, and that is a less denser here. A similar case, the less denser here is more denser than here. And you see that carefully, the gap between two electric field is very less actually. There is a more than that point. Okay, from starting from positive ending to negative. So here is a more dense, there is a less dense. Okay. Now that's also equipotential surface. Equipotential surface. Now arise another question. If I draw the next line of that diagram, how it look like? Now next line actually look like this. Sorry, that's not a good diagram actually. Uh, if I cancel these two, very poor drawing. Okay, if I join these two lines, okay, and I think you understand that. Okay, the stove is the stove. Okay. So get the continuation of equipotential surface actually. See the very carefully the continuation of potential surface, and you see the next diagram clearly understand. There is a plus. Suppose that is a plus 10 coulomb, and that is a plus 1 coulomb. Okay, and why these are opposite polarity? You see that very carefully. Electric field, that line represents electric field. Okay, that's that is outward direction, and here be the also the outward direction. These are outward direction. So create neutral zone here at that point. But in that case, we diagram carefully. So neutral zone either this side or that side. But if the more actually the near the negative charge actually here. Okay, if you know that actually neutral zone creating negative charge, you know that actually the concept of that neutral zone, where the neutral zone place. Actually, discussed that concept in previous lecture. Okay, so now here the two charge is positive, one is plus 10 coulomb is much greater than of 1 coulomb charge, and that is a neutral zone point. That surface is a equipotential surface. Okay, and see the diagram, there is a surface equipotential is much denser at here, much denser at here, but means that opposite of two faces actually. In the plus in opposite faces we get opposite of plus faces of behind actually the opposite of these face is a denser surface. Here is a more denser surface. There is a less denser surface here, and these are continuation, and the field is continuation. Actually potential, sorry, potential surface is continuation. See the very carefully the potential surface. Actually potential surface is scalar quantity. Okay, for understanding I put that mark actually, but potential is scalar. Okay, the marking for that actually for understanding. Okay, that's potential is not a vector quantity, potential is a scalar quantity, a marking for understanding. Okay, so that is a direction appears direction for the surface is a potential. Okay, equipotential surface look like a egg-shaped surface actually. There is a plus 2, the same charge, electric field both in the neutral zone. Okay, actually see the electric field, and that's the potential surface, the piercing the potential surface at electric field. And me the what is the equipotential surface? The actual potential are the same and every point on that surface. Okay, so write down some notes here. Okay, notes. Put a note actually that gap. So equipotential surface, equipotential surface. uh, Adjacent point that have the same electric potential, that have the mm, electric potential from a equipotential surface, and that actually that how to create a potential surface. If I choose some point, I choose suppose 100 point, we get a 100 point the same potential value. Actually get a surface from there. If I choose the calculate potential from 100 point and that 100 point have same potential, now we join that 100 point, we get a surface and that surface is called equipotential surface. Okay. If you calculate that potential first, okay, and we get some suppose 100 10 100 10,000, yeah, a huge number of point we get, that point have same potential value, and then joining that point we get a surface. That surface is called a equipotential surface. That's very important. First get a surface, that is a equipotential surface. It is not. Actually first calculate the potential and same value potential, now join that surface and we get a finally equipotential surface. First calculate potential, then we get equipotential surface. First get surface, then call that is equipotential surface. Actually be the same, but in case of actually the science behind that, first calculate the potential, now the potential value is the same, and we get join the potential point, actually equipotential point, and then get a surface, that's called equipotential surface. Write that point, actually write that from a equipotential surface, from equipotential surface, which can be either an imaginary surface or a real physical surface, which can either imaginary or real physical surface. Okay, that means a potential at point Vp1, calculate Vp2, choose calculate Vp3, suppose Vp4, and now we get a potential value the same. Suppose Vp1 equal to Vp2 equal to Vp3 equal to Vp4. Now joining this point we get a surface. I'll name the surface P surface. Say the surface name is P. That surface is called equipotential surface because the potential value at any point on the surface be the same. And now draw a surface, that is surface also imaginary line or a real physical surface actually. Okay. Now we calculate work done. Now we calculate work done. Okay. Before we calculate work done, here is another diagram. Suppose we see that here the surface is much denser here. Equipotential surface much denser here. Here is a thin line. Actually now that's the diagram represents, this is a called plus charge or minus charge, that surface also a plus or minus, means they are in opposite polarity. They are in opposite polarities. Okay, so there is opposite polarity. So neutral zone of neutral point at here. Okay, that's why the electric field from plus here, that's minus here. Okay, okay. So but there is a very compact point here. Okay, and like the similar the first diagram, see the diagram carefully here. Near the surface, very dense actually the electric potential surface here. Okay, very dense surface. Now the concept clear, I think. What is the equipotential surface? How do I get that equipotential surface? First calculate the potential and get a some, choose some 200 point. You calculate the potential 200 point, send the potential or joining the surface. Okay, joining the point you get a surface. Now we calculate the work done. Okay, now we calculate work done on the equipotential surface. Here the important note for here, the concept of work done. No net work done on the surface or charge. Here, in case of calculate work done, calculate work done concept. So here, suppose In equipotential surface, the charge, how to calculate work done on a test charge moving from equipotential surface, the same surface, the work done will be the zero. How to get the zero value? That's a very important point actually. Suppose we calculate suppose equipotential surface here. Suppose get a new page. Suppose we choose okay. Choose the four surface. These surfaces have equipotential surface V1, V2, V3 and V4. Okay. Now we choose, and if you say that electric field like this piercing that, you know, join this to dot 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 dot. Now, if you want to calculate a work done, okay, if you calculate a work done concept, so on test charge, so test charge moving from suppose I to F path, I to F path on same surface. There is a path number 1, and choose another path, path number 2. Path number 2. Suppose here the test charge moving from path number 2, that potential surface 3. Okay, that is I, that is F. Test charge Q naught move in that direction, I to F. Here same case, test charge move I to F. That is a path number 2. And here the path number 3, same concept actually, from first surface, that is I to F, from surface 1 to surface 2. Okay, that is a path number 3. And last path, path number 4, you choose from 1 piercing to that is I, that is F, and that is path number 4. We choose 4 path. Now calculate a work done from test charge moving here to there. So we know that work done concept actually, you know, the work done on charge Q. Okay, that is from, we know that if work done, that is equal to force means charge I to F, that is force, okay, time displacement, okay, suppose ds, and that force, that is F equal to Q times E, so Q I to F, that is EDS, and now W by Q I to F, we get EDS, and a W by Q, the actually Q naught, a test charge moving from work done on test charge, W by Q, we get a potential. The final potential minus initial potential, that is equal to W over Q I to F E dot ds. Okay, and see that very carefully, we know that is a same surface, the potential value will be the same. If I choose a path 1, carefully choose a path 1, okay, path 1, not path 2, path 1, so potential value will be the same, so final potential, that is also equal to initial potential. that is a zero potential, means W by Q 0, so W equal to 0 joule. So the conclusion is that if test charge moving from I to A from same surface means same potential value, so work done will be 0. So path 1, so get work done equal to 0. And now choose path 2. Path 2, see the very carefully, that's from starting from here and crossing this surface and jump from this surface, piercing, get final F. And I and F are the same path, means same surface actually. Same surface means same potential value. So path number 2, we get same potential value because the same surface. So final potential also equal to initial potential. So if the same in path 1, that is also a 0 joule. Path number 2. Now the path number 3, starting from surface 1, ending from surface 2. Surface 1 to surface 2. That's very important because there is a difference between potential. There is a difference between potential, and that difference is final potential is not equal to the initial potential. If there is not equal, so there is a work done is greater than 0. So work done is present in path 3. And similar path 4, see very carefully, starting from one surface and 2 and ending from 2 surface. Similar condition, if two different surface means two different equipotential surface means two different potential value. So not equal, so work done is greater than 0 joule. Means the work done actually present actually. Okay, work done scalar quantity present actually. So here the conclusion is that if a test charge moving from same equipotential surface, the work done will be 0. If a test charge moving from one surface to another surface, the work done is present. Okay, clear the concept. So now write the notes is the work done by the charged particle. If you want to write the notes, pause the video and write that. Otherwise, you can also write your own word. Okay, that's very better for understanding your concept. If you write in own notes. No net work done. So concept is as a no net work done and on a charged particle on a charged particle by an electric field when the particle moves from when the moves from I to F. Okay, I to F. Actually, work done is positive work done or negative work done. This depending on value of potential. Okay, in that case, is potential 0 joule means either positive work done or negative work done. Work done is scalar quantity, so magnitude is important actually. So if a positive work or negative work, okay, that depending on the value of potential, higher potential to lower potential, charge move from higher to lower potential or lower to higher potential. That's the very important for work done is positive or work done is negative. We choose a 4 path from test charge. We choose 4 path. Okay, choose 4 path. The test charge Q not move from I to F. Higher potential to lower potential to higher potential, or same potential value also. Okay, clear the concept. How to calculate work done on test charge and value of work done on same surface or different surface. Surface means equipotential surface. Okay. Now calculating potential from the field. Calculating potential field. Okay, that is a electric field. This line represent electric field. These are not actually potential surface. That line is a electric field. Calculating potential from electric field. How to calculate value of potential if you know the electric field? Actually, concept is that. Suppose we bring a test charge plus Q naught, move I to F path. Okay, so gap between two electric field line is delta X, that is E. The red color represent electric field. Okay, that is not a potential, not confused. Okay, now calculating work done. Okay, suppose you see that very carefully on the point line, so ds vector in that direction, and that is a test charge. When test charge is here, so electric field actually in that direction. So force and field both are in same. F equal to Q naught times E. Both are vector quantity. So consider, note that, consider arbitrary electric field. Arbitrary electric field. Okay. A positive test charge, charge move from I to F at any point, at point, suppose point be the P point, that point P at any point of the path that's the green color line. Green color line represent the path. The path is test charge moving from I to F path. So force is, and point P we get a electric force. Electrostatic force is Q naught times E test charge. So the work done, okay, work done by the particle by the field. Okay, here the work done by the particle by the field, by the field on particle move, I to F. So work done very simple. Okay, if the work done W, that is a dW, that is equal to integration of I to F. So force time displacement. Okay, so and we know that I to F, that is Q naught times E dot ds. Okay, Q naught is outside, I to F, so E dot ds. Okay, and that W, if I indicate this, if I indicate W, we get W, dW indicate W. So W equal to Q naught I to F E dot ds. So W over Q naught, that is equal to I to F E dot ds, and W over Q naught means potential different. So Vf minus Vi, that is equal to W over Q naught with I to F E dot ds. Okay, if I say that is, if a charge from infinite to finite in reference configuration to any value actually. Okay, so a charge move from higher potential to lower potential. Suppose the important note, Okay, so that is a I electric field E, and that is a F. Okay, so that is a high potential surface, so low potential. So I to F is low potential surface. That's the actual electric field in that direction E. That's the surface. Okay, so the gap between these two is a delta X. Okay, so V I is much greater than VF. So get a minus potential, that is equal to minus, sorry, not minus, actually plus I to F E dot ds. Next line we get V equal to minus I to F E dot ds. If small value minus bigger capital value or bigger value, we get a minus. So box that the potential value. Okay, move between I to F between adjacent equipotential line of the uniform of electric field parallel to the field lines. Okay, so that concept is like that. If I add the note is important point is, so that we move actually test that move, we move between I to F to F. Okay, between adjacent equivalent, between equivalent line in uniform electric field, uniform electric field parallel to the field lines, the parallel to the field line. Okay, now if I get a integration actually point, the integration of V is that is equal to minus. Okay, so E dot ds, we know that is EDS cos theta, is both in same direction actually. Okay, the surface is, because the surface now actually this. Okay, the surface actually now the surface. Okay, that's the surface. So ds in same direction. Okay, that's the potential surface, equipotential surface in same direction. The potential surface from both the same direction. So EDS cos theta, EDS cos theta, and theta be the 0 degree. So that is cos 0 be the 1. So EDS. So you get a minus I to F EDS, and V equal to minus here. So E I to F get ds. So integration of ds is a S. So V E, and if I get these are the final point to minus the displacement of two surface, actually the delta x. Okay, so S final minus S initial, so difference is a delta x. So that is a delta x. These are the delta x, gap between two electric field lines. So that is a delta x. Okay, so if I that is delta x, that is a delta v. Okay, so similarly with the concept we get a delta v by delta x, that is equal to minus e, and in differential you know that dv by dx, that is equal to minus electric field. Okay, clear the concept. Actually test charge moving from I to F, okay, choose an arbitrary path actually. Okay, in electric field. Okay, so calculate potential from the field. I think clear the concept. Okay, so next class we discuss a new topic, continuation of these. Okay, if any doubt in that section, so ask in comment section. I will try to give the answer. So remember, we do practice, too much practice. If you practice regularly or vigorously, and the concept is very easy, not tough. Okay, very easy, and just do your homework. Okay, for best of luck for your exam. Thank you.